last time, we defined these LP spaces of functions for which the integral of the pth power of the absolute value is finite, or in the case of p equal to infinity, the essential supremum of the absolute value of f should be finite. And then we started with one example we just wrote down a function from R to R and wanted to check whether this function was in L1 or in L2. And we finished the first half last time, so we showed that this function is in L1. Basically, we showed that the integral is finite. And today we're going to show the second half, which is we're going to show that this function is not in L2. So to prove that this function is not in L2, well, if it was in L2, then the integral of the square of f would have to be finite. So we have to show that the integral of the square of f is infinite. And that's going to be easier than the first half, where we showed that it's in L1, because okay, we can start similarly to what we've done last time. We can define a sequence Fn to be the characteristic function of the interval from 1 over n to 1 times absolute value of f squared. Okay, so this sequence Fn is basically a version of f where the singularity has been cut off, right? F looks like this. And then if we multiply it by the characteristic function of the interval from 1 over n to 1, it becomes a bounded function. So now it's a bounded function on the interval from 1 over n to 1, and it's also continuous on that interval, so it's Riemann integrable. So for Fn, we can again use the Riemann integral, and then use the fact that the Lebesgue integral is equal to the Riemann integral for such functions. And in addition, of course, the absolute value of f squared is an upper bound for Fn, because Fn is just the same thing as f, but set to 0 between 0 and 1 over n. So we have this inequality. And now from the monotonicity of integrals, we get that integral f squared is larger or equal than integral Fn. And now this integral of Fn, that's just the Riemann integral. So let me write it like this: integral from 1 over n to 1 Fn dx. So this is so now this is a Riemann integral, which means that we can use the fundamental theorem of calculus to compute the integral. Because, okay, this is just the integral of x to the minus 1/2 from 1 over n to 1. So we just use the primitive and we get, oh, it's not, sorry, it's not, it's the integral 1 over n to 1 of 1 over x dx, right? Because we square it. And now this we can compute. This is just log 1 minus log 1 over n. And log 1 is equal to 0. So this integral is just the logarithm minus the logarithm of 1 over n. And now if we send n to 0, this goes to infinity. Okay, but what we started with was the integral of f squared, right? So the integral of f squared is larger than this for every n. So we can send n to infinity and then conclude that this integral has to be infinite. And this means by definition that f is not in L2. Okay, so this was one example to show how one deals with these definitions of LP spaces and how just with what kinds of functions lie in LP and what kinds of functions are not in LP. So in this example, the problem was the singularity at 0, right? So if a function grows too fast at 0, then this is not in LP. And the value of P for which it's included or not included depends on the how fast the function grows. So for example, this function was in L1 because the singularity was benign and it didn't, and x to the minus 1/2 doesn't grow that fast. But it's not in L2 because for L2 it grows too fast. Because you square it and then the growth becomes even worse and then it's not in L2 anymore. Okay. So this was one example, and now, okay, first, are there any questions about definitions of LP spaces or this example? Okay. Okay, then we have one remark. So these LP spaces, they're natural things to define, but they have certain issues. So for example, the LP spaces are not vector spaces. Because expressions like f plus g make no sense because f and g can be infinite. So because f could be plus infinity at some point x, and g could be minus infinity, and then f of x plus g of x would not be defined. So this is one problem. Another one is this LP norm that we defined last time. That's not actually a norm. Because if the LP norm of a function is 0, then the function does not have to be 0. So the LP norm is this integral of f. But if this integral is 0, we can only conclude that f is 0 almost everywhere. But it doesn't have to be 0 everywhere. So that's why this thing that we call LP norm is not actually a norm on this space LP. These are two issues, and we're going to deal with them later. And we'll see that there are ways to resolve this. Okay, and for the rest of this chapter, we'll study these LP spaces and try to solve these two problems, more or less. So what we're going to do next, first we're going to take a small detour to real analysis and introduce convex functions. So let I be an interval in R. Then a function f from I to R is called convex. If the following holds, f of tx plus 1 minus ty is less than or equal to t times f of x plus 1 minus t times f of y. For every x and y in I, and for every t between 0 and 1. So this is the definition of a convex function, and the picture you should have in mind is this. So if the function looks like this, f, then what does this inequality mean? Okay, say x is here, y is here, then here we have f of x, f of y, here we have f of x, here we have f of y, and now at this point, tx plus 1 minus ty, where t is between 0 and 1, that's always going to be a point between x and y. So, for example, this could be here. Tx plus 1 minus ty. Okay. And now now this point is f of tx plus 1 minus ty. So this point would be the left-hand side of this inequality. And now this right-hand side is a linear combination between f of x and f of y. So what the right-hand side is the following. You draw a line segment between these 2 points, and then this point here would be t f of x plus 1 minus t f of y. Okay, so this is so the blue bit is the left-hand side of the inequality, the red bit is the right-hand side of the inequality. And from this picture you can see that, yeah, the definition of convex says that the red dot should be above the blue dot, right? The red thing should be larger than the blue thing. So really this definition means that the function has to be curved like this. If you draw a line segment, then the function itself should be below the line segment, basically. That's what convexity means. And of course, one example that's relevant for us is the function mod x to the power p, where p is larger than 1. That's a typical example of a convex function. Okay, and this next remark gives some properties of convex functions that are useful and that we're going to use later on. The first one is if f is twice differentiable, and the second derivative is non-negative, then the function is convex. So this should be clear from, I guess, first year courses. But yeah, this definition of convexity is more general because the function does not have to be twice differentiable for this definition. 2. One can show that if f is convex, then f is continuous. And 3, if f is convex, then the following is true. For every t in I, there exists a positive number alpha such that f of x is greater or equal to alpha times x minus t plus f of t for every x in I. So this last statement, we're not going to prove it, but I'm going to draw a picture and it should be fairly clear that this is true for convex functions. And the proof is really just the calculation. You start with this, and you can derive this. It's elementary, but it's quite lengthy, and I don't want to do it on the blackboard. So if we have a convex function, then this means that, what does this mean, okay? So this inequality has to hold for every x in I. So t is fixed, alpha is fixed, x varies in the interval I. And f of x has to be larger or equal than alpha times x minus t. So this is a straight line, right? If x is a variable and alpha and t are fixed, then this is a straight line. And f of t, that's just a point. So if we pick a point t, then this inequality means that f of x lies above this line for every x. So just like, yeah, lies above this line. So this line would be alpha times x minus t plus f of t, right? And f of t would be exactly this value where it touches. And it's fairly clear that you can always find such a line that lies below, that completely lies below the function, if the function is convex. So this one can always do, and we're going to need this. We're going to need this in the next proof. So the next lemma is a pretty important inequality between integrals. So let x sigma mu be a measure space. And we assume that mu of x is 1. So the measure of the entire set is equal to 1. Then let f be a real valued function on x, and let f be integrable. So that's lowercase f, and let uppercase f be a convex function. And then the claim is that uppercase f, lowercase f followed by uppercase f is measurable. That's clear because uppercase f is continuous. And if one of the two following conditions hold, first one is lowercase f followed by uppercase f is bounded below and the second one is this composition of functions is integrable. Then the following inequality holds. Uppercase f applied to integral f d mu is less than or equal to integral lowercase f followed by uppercase f d mu. Okay. Okay, so in short, if the measure of the entire space is 1 and we have a convex function, then we can pull this convex function out of the integral and we get this inequality. And this is going to be really useful in the context of LP spaces because, as we noted, this function mod x to the power p is convex. So we get certain inequalities for functions in LP spaces. And this inequality is the reason why we introduced these convex functions in the first place. And the proof goes like this. Okay, so by assumption f is integrable, so the integral f d mu is finite. And we call this integral capital M. Then now we use convexity of this function uppercase f. And we're going to use this remark, point 3 of remark 5.6. So there exists an alpha such that uppercase f applied to f of x is greater or equal to alpha times f of x minus m plus uppercase f of m. Right, so this is precisely this inequality with t equal to m. And x replaced by f of x. Okay, so we have this, and this holds for every x. In the measure space x. Because for every x in x, lowercase f of x is some real number, and this uppercase f was defined on all the real numbers. So this inequality just holds everywhere. Okay, so we have this. And now because this holds for every x, we can just integrate this inequality. And then some magic will happen. Right, so if we integrate this inequality, we get the left-hand side becomes the integral of lowercase f followed by uppercase f, and then this is greater or equal to integral alpha f of x minus m d mu plus integral f of m d mu. And now we just simplify the right-hand side. So now we can use linearity of integrals to simplify this right-hand side. So on the right-hand side, the only thing that depends on x is this, right, f of x. Everything else is just constants that we're integrating. So we can do the following. This first term becomes alpha times integral f. The second term this alpha times m, I can pull in front of the integral if I want to, and then I just have alpha times m times integral d mu. And I can do the same in the last term, f of m times integral d mu. But now let's look at our assumptions and our definitions. Our assumptions said that mu of x is equal to 1. So this integral is equal to 1, and this integral is equal to 1. And then m was defined just to be the integral of f. So this integral is equal to m. So really what we have on the right hand side is alpha times m minus alpha times m plus f of m. So alpha times m cancels, and the only thing left is f of m. And this is precisely the inequality that we wanted, right? This composition of functions should be greater or equal to f applied to the integral. So this is the proof. Okay, and the rest, so yeah, the rest of the section will mainly consist of proving more inequalities similar to this one. And they're all going to come in very handy, and they're all really useful, as you will see on the problem sheets. So the next lemma sometimes called Young's inequality. This is again a statement just about real numbers. There are no integrals involved. But we're going to use it later to prove an inequality for integrals. Okay, so Young's inequality says that if we have two numbers, p and q, between 1 and infinity, and they satisfy the following equation: 1 over p plus 1 over q is equal to 1, then yeah. Then for all non-negative numbers a and b, one has the inequality a times b is less than or equal to a to the power p divided by p plus b to the power q divided by q. And the proof of this uses convex functions again. So okay, if either a or b are 0, then this inequality is trivial because the left-hand side is 0. So we can assume that a and b are both non-zero. And then we can do the following. Let f of x be the function minus log x. Then this is a convex function because just because you can compute the second derivative, and the second derivative is 1 over x squared, right? If you differentiate minus log x twice, you get 1 over x squared, and that's a positive function. So the second derivative is positive, so f is convex. Okay, so if f is convex, we can do the following. We get the inequality log of a to the power p divided by p plus b to the power q divided by q, and that is greater or equal to 1 over p log a to the power p plus 1 over q log b to the power q. So this just comes from convexity. This is basically the definition of convexity for f, where this is t, so 1 over p is t, and 1 over q is 1 minus t, if you want. So that's why we needed this assumption 1 over p plus 1 over q equals 1. And now again we simplify the right-hand side. The right-hand side, by the laws for logarithms, this is 1 over p times p log a plus 1 over q times q log b. So 1 over p and 1 over q cancel, so this is log a plus log b, which is the same as log ab. I now just take the exponential on both sides, and we get the desired inequality. And this is actually a really neat trick. It would be really difficult to prove this inequality without this trick using the logarithm. But if you use the logarithm, it's immediate. It's just a simple calculation. And these, in the remainder, these exponents p and q, which satisfy 1 over p plus 1 over q equal to 1, that's going to appear more often. And we're going to call such numbers p and q conjugate exponents. So if 1 over p plus 1 over q is equal to 1, then P and Q are called conjugate exponents. And now you might wonder, why did we prove this inequality? That's just real analysis. Well, the next theorem is the reason. It's called Hölder's inequality. And it's arguably the most important inequality between integrals that there is. Really, people use it everywhere. In every paper about differential equations, someone uses Hölder's inequality somewhere. So let X sigma mu be a measure space. P and Q between 1 and infinity with 1 over P plus 1 over Q equal to 1. And let F be an LP of X sigma mu and G and LQ. Then F times G is in L1. And integral of mod Fg is less than or equal to LP norm of F times LQ norm of G. And the proof relies on Young's inequality here. So okay, so in the proof we're gonna differentiate two cases, because we're allowing P and Q to be infinite, right? And L infinity was defined differently. There was no integral in the definition of L infinity, so we're going to focus first on P and Q finite. And then in a second step, we're going to treat the case where P or Q might be infinite. Okay. So if P and Q are finite, first, without loss of generality, we can assume that the LP norm of F and the LQ norm of G are strictly positive. Because if they're equal to 0, then both sides of the inequality are just 0. So so then it's trivial. So we can assume that they're strictly positive. Which means that we can divide by these norms. So Young's inequality here tells us that the following holds: F divided by norm f times g divided by norm g is less than or equal to 1 over p times f divided by norm f plus 1 over q times g divided by norm g. Okay, so we're taking f divided by norm f and g divided by norm g as a and b in Young's inequality, and we just get this. And that's an inequality that's going to hold for every x, right? If we plug in f of x, g of x, and so on, then this is going to hold for every x because of Young's inequality.
What happens to the powers? It's like a to the p and b to the q.
That's true, I forgot that. Thank you. Yeah, so we have exponents p and q on the right-hand side, sorry. Yeah, now because this holds for every x, we can just integrate this inequality. And because norm f and norm g are just constants, we can take them out of the integral, and we get 1 over norm f times 1 over norm g times integral mod fg d mu on the left-hand side, and this is less than or equal to 1 over p, 1 over LP norm of f to the power p times integral mod f to the power p d mu plus 1 over q, 1 over norm g to the power q times integral mod g to the power q d mu. And now again magic happens. So let's forget about the left-hand side, look at the right-hand side. Here we have integral mod f to the power p. That's precisely, by definition, that's the LP norm of f to the power p, right? And this integral of g, by definition, is the LQ norm of g to the power q. So this integral cancels this LQ norm, and this integral cancels this LP norm. And on the right-hand side, we're just left with 1 over p plus 1 over q, which is 1.